In the last lecture, I gave description of the hardware used in a nuclear magnetic resonance. In particular, the values of various parameters that are involved, and those values are important in designing various operations, as I will describe today. So let me rewrite some of those elementary things. The Hamiltonian is just made up of two simple kind of interaction. There are magnetic moments corresponding to individual nuclei, and they interact with a background field. This background field has two components. One I will call B0, which is static. It actually quite large, polarizes the nuclei, and then there is a AC magnetic field at radio frequency, which I will call B1. So the magnitudes, this is R. The static field is quite large. It is of the order of few Tesla, and the radio frequency field is much smaller, typically about 10 raised to 4 in magnitude. We'll see that this is actually chosen to decide the length of the pulses which are implemented as logic operations. So this is the one term, and the other term is a kind of nearest neighbor coupling between two spins, and the normalization is a kind of convention, but I am writing it as some coupling Jij and dot product of the Pauli matrices. The 4 is a convention because a qubit is represented by 1/2 of the Pauli matrix operator. That's S equal to half state. So that is put in there explicitly. And this term is much different than the static terms, but this is of a different character. So this is, let me say, this is has one property, that this interaction is always on, unlike this time-dependent radio frequency. It is there throughout the whole calculation, and because of that, to implement specific interaction, you have to start and stop at the right time. Otherwise, you don't get the correct transformation. And the magnitude of this J is a chemical shift, which I mentioned last time. And compared to this background field, it is a million times smaller, few parts per million. Okay. It varies depending on who is neighbor of who and what are the neighboring environment of various spins, etc. But this is the typical magnitude. So we have to keep this in mind. And now the question is, what can you do with such a system? So yeah, I can actually point out something else also, which is worth keeping in mind, that all these parameters are there, but they also give you an idea about what is the magnitude of the errors, because things fluctuate, and the common features which are included is fluctuations in various terms. By one I will describe. The background magnetic field, it has to address the whole ensemble of the molecules, and it may not be uniform. There are fluctuations in it, and that is a question of technology. And last time I mentioned that it can be made quite small, 1 part in 10 raised to 9 or something like that. So this is one source of error. Then this B1 can also produce errors. So it comes through the rotation pulses which are produced by this radio frequency field, and the calibration of it may not be perfect. Okay, you want to rotate it for certain duration, but the actual duration might be little different, or the magnitudes are of some size, but they can go off and on. And this is not required to be as accurate. That's this B0, which is 1 part in a billion kind of accuracy. Here what will happen if the calibration is not uniform, then some spins will respond and some spins will not respond. And we don't require all the spins to respond simultaneously to produce a signal. Well, the signal will be a little bit smaller, and then it will produce a certain kind of fluctuations which are more easily managed. So this is the error in this. This chemical shift are properties which are properties of the molecules, and they are quite precise, because well, molecules do vibrate a little bit. So the bonds change in length, and some interaction will go there, but that part is not that important. What is more important is this magnetization which is produced from the various magnetic field. It decays in time. I gave 2 time scales, T1 and T2, in the last lecture, and this is a more general effect of the environment, not just of the neighbors, but it is going to happen. And we have to worry about how much this error will be during the calculation which you perform. So the overall now specification is of the apparatus which is available in the hardware, and the observations by doing many experiments is that do ultimately do all the operations and signals extracted from the density matrix. Um, and you can get it down to something like 1% level from all these various kind of errors. Of course, you can ask that can you do better, and the answer is yes. Many of the techniques which I went through under the label of error mitigation were actually developed for NMR, and they have been carried over in a more general framework, and you can improve it a little bit, but for the main use of this NMR system, which is study of chemical and biological structures, this is quite good. Okay, this kind of accuracy, and that's the overall picture. And many of the experiments which have been done of the order of 10 qubit systems, that is how far it has progressed, and they are quite comfortable with having an error of the order of 1% because it demonstrates that the algorithms are working. That's good enough. Okay. So now comes the question of simplifying this Hamiltonian in a particular setting, so that is done in dissolving this particular molecule, whatever it is, in some liquid, and keeping it dilute. So the molecules basically act independently with the external field, and whatever signal they produce can be combined with a statistical fashion. But this scenario actually further simplifies the Hamiltonian that we need to work with. Okay. And that doesn't do too much to this. It's just a single spin part, and the liquid is not going to do anything to it, but it simplifies the second term. So now one can ask what can happen to this two-spin coupling inside a liquid, and it has two parts. One of them is a direct dipole-dipole coupling, and it depends on the positions of the two nuclei, which is Ri minus Rj. it's not actually just the modules, it depends on the direction as well. So it depends on one nucleus is here, the other is here, it can be this orientation, that orientation, all kind of things can happen. But what turns out to be quite useful in case of liquid solutions, that the orientation can move around. The molecules tumble in many different ways. It's a completely flexible system, and in that situation, this dipole field averages to 0. Then the liquid has low viscosity. That means the molecules can move around very easily. Okay, so this is just and if you want to write down an explicit dipole field, you can write it down during spherical harmonics, and it's a higher order harmonics, and the average of the spherical harmonic is basically 0. The only one which has non-zero contribution is the angular momentum 0 S wave case, but dipole is a higher order. And any higher order will average to 0 once you take into account all possible directions. So this coupling is a direct component, but it goes away. But then there is an indirect component. And the NMR people basically just refer to it as a J coupling. This J is a common notation in this whole literature. How does this arise? It arises because the nuclei are not independent. There is actually a chemical bond between the two. So this is just a nearest neighbor interaction. This will be there for any two arbitrary free dipoles. Whether there is a bond between them or not doesn't matter. But because there is a bond, the nucleus interacts with the electron wave function in the bond, and the two electrons which make up the bond, they are tied together in basically a singlet. There is no polarization or angular momentum coming from the electron, and so the second electron has a connection to the second nucleus, and there is a indirect coupling, but basically means that it goes through the electrons which form the bonds. And this coupling is fixed. That is actually the coupling which is responsible for producing the chemical shift. So that is that component is going to remain. So yes, it is sigma I dot sigma j, but only between nuclei which are connected by a chemical bond. But even that simplifies in the sense that you can have scenarios where the rotation frequencies of these two nuclei around this particular magnetic field are different. Okay. So, if you write down this sigma I dot sigma j, the usual notation is a dot product. So, you will write down xx plus yy plus zz in terms of Pauli operators. But when the coupling is weak, which basically says that this term is much smaller than the first term. Yeah. Yes. Yeah. This is just an expression of a Cartesian dot product. There is nothing more complicated than that. Spins of the two nuclei. If you want, I can put labels on this. And these are just the Pauli matrices which will form this particular dot product. Nothing complicated in that. So, when this coupling is weak, that means this term dominates, or equivalently the frequencies of the two nuclei are very well separated, which can be written as some frequency omega of one nucleus and omega of the another nucleus. The spins are going to rotate at a very fast rate about the direction dictated by the large term, and that by definition is the z direction. Okay. And when the two nuclei are rotating very fast and this term is compared to the large term negligible, this averaging will destroy all the off diagonal components of the dot product. Because both of them are rotating at some fast rate. The rotation direction is the z direction, and if you look at a kind of time averaging, this off diagonal term, the x and y components, will undergo so many rotations during its evolution under J that it basically just averages out. And the result of that this off diagonal actually all the components average out, but the z component is fixed by the orientation of the magnetic field. So, average of z is just remains z, but average of x and y at rotating at very high frequency is 0. And so this coupling then becomes simplified, and that is just H J, which is this part of the coupling. It's just written as J I J by 4 Z I Z J. And this is now the simplified Hamiltonian, and it is used to do all the programming and the calculation of whatever operations you want to perform on this particular system. And it's quite simple in the sense that the Z Pauli matrix actually appears most of the time. It contributes in the interaction, it contributes to the component along this static field. The only thing which has x and y is remaining in this radio frequency field. So if you remove this radio frequency field, it is just a certain distribution of the Z components of various nuclei, which can be very well described by some thermal distribution, some eigenvalues, whatever they are, and that is the equilibrium state. When you turn on this radio frequency field with various strengths, you disturb that equilibrium. So this equilibrium and we are going to use these Z components to label all the eigenstates. Something is up, something down, nothing more complicated than that. Okay.
So,
yeah.
these omega i's are the RF frequencies.
They are the frequencies in general for this static field.
So, you're talking about this precisions, right?
Yeah, so omega I are, this one has a different frequency. I'm just going to call it omega. But I and j, when the subscript appears, it refers to the nucleus frequency under this background field.
So, how does the well separation of them ensure that they average out? I mean, upon precision, the average is moving as a number. What is the importance of that?
So you want to, basically this is the interaction between the two spins, but both of them are rotating at this their own frequency, omega I and omega j, and you want to look at it under a time evolution which is dictated by this j. And so when j evolves, say by some one oscillation or some transition frequency, this omega I and omega j have undergone many different or many more rotations. And so if you take any spin component and just average it out, this one you want to measure it over a certain time, but in that time it has gone around many times. So you have to ask what is the average of this xi, xj, yi, yj going to be in under that situation, and they become 0. So they are precessing around the z axis. Okay. Fine. So this is a kind of summary, and now we can address individual components of the algorithm one by one. So simplest thing is to look at single qubit rotations. Okay. For that I will ignore this j coupling for the calculation, single pin rotations are basically produced by the effect of both B0 and B1. B1 is absolutely necessary because B0 will only give the Z state and it will polarize it, but this is going to be in the XY plane and it is going to rotate. And these rotations are performed by the resonant structure which is buried inside the simple looking Hamiltonian. So let me write down this H, just call it 1 qubit part. What is its generic structure? And I will just drop this label I and J, which label keeps track of which nucleus is there. It's one particular nuclei, and it has a frequency omega 0 by 2, which is coming from this B0 component. Half is again the spin normalization. It's a convention because spin is half the polymetrics. And then there is a component coming from this radio frequency field, and which I can write in most general form as the magnetic field, which is given by this direction or x and y and the corresponding phases. Okay. I have picked a convention so that one of them is cos and another is sine, but it's just a question of forming the corresponding dot product. It is all mu dot b, and you have to pick a starting point, whatever t0, so one of them becomes cosine, the other becomes sine. Nothing fancier than that. And now we want to calculate the evolution under this particular Hamiltonian. We know the Schrodinger equation, so it's just solving this is, you can do it directly, no problem, but then there's a time dependence sitting inside this H, and we would like to get rid of it, so the solution has a simpler looking form. So you transform to what is known as a rotating frame. Which is defined by this explicit phase e raised to I omega t by 2 coming from essentially this radio frequency field. What is omega is same omega sitting over here, and in the new frame that rotation is kind of factored out. It's just a change of variable. There is nothing more complicated than that. But we will see the algebra looks much easier once you now go into these new variables. And so let me do that. Yeah. We want the time evolution of this object. What is it? Well, you just have to back substitute in this particular equation. So you get phi by multiplying by this quantity. So the one contribution is just this change of variable for h, that you calculate phi t by multiplying by this particular factor, but the other side has psi, which is e raised to minus omega t by phi. So the h undergoes basically a unitary transformation according to this rotation matrix. But there is a second term, and the second term is nothing but direct dependence on this omega in the definition of phi itself. There is a time derivative of phi, and I have to take into that structure as well, and that time derivative basically gives this time omega by 2. There is a minus sign coming because there is an I here, there is an I here, and I square will give minus sign. Okay. So this is now the modified equation, but the purpose of doing this is that this equation becomes time independent. T disappears, and then we can do all the integration in a very simple fashion. So I think I lost the important factor, that this is in the z direction. The rotation depends on the eigenstate. Okay. So now let me calculate this. I have to perform this unitary transformation on both x and y. Okay. So what does it look like? E raised to I omega t z by 2, and then x, and e raised to minus I omega t z by 2. Now we can do very simple jugglery, that x and z anticommute. So I can take this onto the other side of the equation by flipping the sign of z. So this is e raised to I omega t z times x, and then I can expand. So this is cosine omega t times x, and then the direction. So plus I sine omega t times z, and then x, and that is we can now calculate. This is the Pauli algebra. Z times x gives you y. Okay. And you can do the same exercise for the y term. So that will become cosine omega t times y, and then y times x will give minus z. So this sign will be opposite. So it will be plus sine omega t times x. Okay. And now we can simplify this whole jugglery. Not huh? Zx is equal to plus Iy. cyclic product of Pauli matrices. X, Y is Z, Y, Z, Z, X, whatever it is, gives an X Pauli matrix. Anyway, so now we go back to this equation, I del by del T what is this? So you have to put this extra factor of cosine and sine together with this, and you will find that there will be cos square omega t coming from here and sine square omega t coming from here, which is equal to 1. That is the coefficient of x. And the coefficient of this y is, one of them is cosine times minus sine, the other thing is cosine times plus sine, and it cancels. And the result is basically simpler. So now it is omega 0 minus omega by 2 times just the x term with whatever coefficient in front was sitting there. This term just goes through trivially, that is the omega 0 by 2. This e raised to I z doesn't do anything to it, but this is also proportional to z. So what we have done is effectively reduce the frequency from this background field omega 0 contribution by this value omega, and this stuff is time independent. So the integration is trivial, just have to exponentiate this. Okay. So solution is e raised to minus I, I have to put a corresponding factor, but this minus I is coming from this stuff, the usual thing, and this can be treated as some constant. And that is, there is a phase, depend on the various qubit components, and there is something proportional to time. Okay. So this has this resonant behavior buried inside it. Okay. How we will see it? Well, go and look at again the magnitudes involved. So G comes from this component B1, and this first term comes from the component B0. But the B0 is fixed, so the value of omega 0 is fixed. The small omega is tunable. It's the frequency of the RF field. And so we can ask the question, what happens when omega 0 is very close to omega, which will correspond to the resonance, and the non-resonant part will be omega 0 is far from omega. So in general now, this evolution corresponds to rotation in a magnetic field, and it has two parameters. One is the direction of the field and another is the angle of rotation. So we can just write it down. So let me follow some notation. Yeah. Yeah, it's just a change of variables. In this modified variables, this is the equation. That is agreed or not? Okay, that's all. I don't want to say anything more than that. But now you interpret this as a rotation of this particular spin half vector in a background field with some direction and some angle. Okay. So rotation direction or axis actually. No. Well, you just have to normalize it. The magnitude will give you the angle. Okay. So what is the unit term which you can write down, and it is written in some by factoring out something term, but that is so I'm going to remove this factor of this, whatever is multiplying z to the other side, and then normalize this vector. So it is 1 plus 2g omega 0 minus omega square. And the rotation angle is the remaining part of the magnitude, which I have kind of scaled out from the definition of the axis, and it is written again with some convention, whatever you want to call it. Let me call it theta. So the t times the square root okay, it's written in a different notation, but that's fine. Omega 0 omega by 2 whole square plus g square. Yeah.
Omega naught is corresponding to the static field.
Yes.
But if V naught is DC, omega naught should be 0.
It's not 0, it is whatever parameter is coming from the static field. The equation I am solving is defined by this particular Hamiltonian. This component is there. It's not disappearing. It went into a simpler form, but all this change of variable basically reduced to that I can just treat it as a overall constant without worrying about time dependence.
That is, how are we associating frequency to a DC field?
Frequency with?
That omega naught we are corresponding it with the static field. Right?
Yeah.
What is the equivalent? Because in DC field, in DC case, frequency will be 0. I mean, there is no.
Okay. This is just a standard convention. Hamiltonian has units of energy. And I am writing Planck's constant h cross equal to 1. That is where this omega gives a particular value. It's energy. But everything is written in frequency units in all this NMR literature. H cross is, you can put it back, but it's scaled out from all over the place. Okay, and this is the angle, now whatever you want to call it, there is a factor of 2 buried inside somewhere because it's spin half, but that is fine. And this I is part of the evolution, where the evolution will be e raised to I theta times this unit vector. And it basically, well, just some set of values, but these are the two parameters which describe this rotation. So now let us look at two specific cases. One is omega 0 minus omega is much larger than G, which means you are sitting away from the resonance. Okay. So then I can throw out all the terms which involve G. What I have is a rotation about Z produced by this magnetic field, which was B0. Essentially, that's what is left. And that is kind of trivial. It is going to precise about the magnetic field irrespective of everything else. And this is just a trivial phase, nothing much is happening. Even though it is a rotation, this axis n is the z axis, and it doesn't give any observable consequence. But on the other hand, you go close to the frequency by tuning this omega, and then I have to throw out the other term. Okay. So essentially this becomes very large. I can ignore one and I can ignore that one as well. So this n is now along x direction. And the angle theta, well, I will throw out this thing, and that is equal to just g times t. So this is the resonance phenomena. If I go close to the background frequency, the RF field will induce a rotation about the x-axis of the original spin, which was along z. And if you rotate the z along x-axis, it will go around on the Bloch sphere. How much it will go around the Bloch sphere is dictated by this g times t, where t is the duration of the pulse and g is the magnitude coming from this B1. Okay, I just wrote it down as a coupling over here, but this is essentially the dot product of mu with B1. Okay, so magnitude of B1 and here is the numbers which I put in become relevant. If you take B1 to be of the order of a millitesla, it will tell you how long this pulse would be if you want to go around on the Bloch sphere. And those pulses are designed accordingly. Some B1 you have decided for the choice which you make, and all you have to know is the relevant scale between B0 and B1. It's about 10 to the power 4. So while you make 10 raised to 4 rotations in along this background B0 field, this one rotation is at a rate which is 10 to the power 4 smaller. And that actually dictates how many of these operations you can perform within a certain time interval. And typically, these pulses of B1 are in millisecond or smaller. That is a range which you end up with. And on top of that, they can be shaped by an external program. And what it means that you can make this G time dependent. It's still going to give you a rotation, but now it will not be just some square wave kind of simple to describe instruction. It can be time dependent, and this is also typically done to cut down on the error. So one of the error mitigation technique is based on that, and that is all connected with the fact that imperfect calibration of B1 will produce some error, and you juggle around various things to make it as smooth and well behaved as possible. Okay. So this is one part of the story. It describes where the resonance is coming in and how it is important. And resonance is responsible for generating all the 1-qubit transformation. Okay. So before going to the 2-qubit thing, let me describe another role which is played by the same RF field or the RF coil, more to be specific, and that connects to measurement. And the principle involved inside here is very simple. It is electromagnetic induction. It works two different ways. You apply field, and object rotates, which is what we call a motor. But you can do the reverse. let the object rotate, and it will produce the field, which we call dynamo. Okay. So the same RF coil is used for two purposes. One, you drive it with that field B1, it will perform this rotation and transformation. But on the other hand, you don't apply any RF field, you make it watch the system. Okay. And the transformation in the system will generate a voltage inside that coil, which you can measure. So it will tell you what is the state of the system and how is the system transformation going to occur. Well, you did some calculation and you have gone out of the equilibrium. Just allow the system to relax back to its equilibrium state. So it has some non-trivial density matrix, which is not the eigenstate of this Z component. It has developed some X and Y components. We allow it to decay. And it will go back to this Z state. So the transformed density matrix is allowed to decay to the thermal equilibrium state, and it produces a voltage in the coil, and you can measure that. Okay. So that is a second use of the same coil. What is this signal? And you can write it down very simply by looking at the evolution. And it's, well, you can write it in many different ways, but it is rather simple enough form. That the density matrix is going to evolve for some time, and the density matrix evolution is just given by this unitary factors of the Hamiltonian, whatever that Hamiltonian was, the total Hamiltonian of the system. And then it will be projected along the X and Y component, because the situation is such that the Z component doesn't produce anything observable at all. So the again some labels, but this is the operator you are going to project the density matrix, because you are measuring this RF voltage in the XY plane, whatever it is. The Z component doesn't contribute. Okay. And that remains true in general. and well, this is some vector in the xy plane. Putting an I in front of one of them is a convention, but it's like a complex number. You can measure it, whatever it is. So the question is, what will this produce? Okay. Now here rho is some general matrix. Okay, we have done all kind of transformation part of the algorithm, but H is the same old Hamiltonian, whatever was sitting in the original term, and the z component of rho is not going to contribute. You are only looking for what are the contribution in x and y direction. And so you have to evaluate that particular structure. And this H contains this overall rotation at frequency omega 0, and that will be part of this Vt. It will appear because of this factor, and that will be a very high frequency. So what the instruments actually do is so the NMR setup combines this V of t with a background oscillator you need to subtract this thing out. So you measure this Vt by essentially shifting the frequency by omega 0 or subtract it out in some particular way of comparing a background oscillator with whatever you see over here, and then Fourier transform. That is because there are going to be frequencies over here. Omega 0 is gone, but that other frequencies of the Hamiltonian, which are now coming from this term. Okay. Now we are in the dynamo mode, so B1 is equal to 0. It's not there. But this chemical shift stuff is there. And what will this transformation will produce? It produces all kind of terms which all are generally written in the frequency language. Something which oscillates with the frequency of omega 0, we subtract it out, and something which oscillates with the frequencies, those corresponding to the chemical shifts. And then what you see are all kind of peaks. So you will get a spectrum something like this. And each resonant is unique because this is going to happen for each value of the spin. The size of the peak will actually tell how many atoms or spins are in that particular state. It could be that some level has many spins sitting there, some has few, and that will decide the height, or actually more correctly the area under this particular curve. And the spectrum comes out very sharply peaked because of the resonance phenomenon. So all this NMR data, they will show figures like this, that this this determines the chemical structure by telling you which elements are producing this particular chemical shift in the chemistry and biology application, or in the quantum computations side. We will get to know the populations of various energy levels.
How do you combine
Hmm?
How do you combine BT with the oscillator signal? Is it a product?
It's an oscillating signal, so you are going to go into the Fourier transform. You essentially multiplied by e raised to minus I omega 0 t and combine. When you perform the Fourier transform, you just remove that particular part. I mean, you are going to do a Fourier transform on this, and you can put e raised to minus I omega 0 t extra in there to just cancel it out. That's all. Fourier transform is necessary because this is what the evolution of the density matrix will produce, and you write it down in brute force. It is just a various oscillating term coming from the definition of the Hamiltonian. And it's all in that Z basis. So it's just energy levels, and you can interpret them as populations of various components at the instant when you are doing the measurement. What you need to keep in mind that this process, so occur at a particular time scale, and this is the equilibration time scale of various energy states, which I had mentioned last time. For the decay, it's the time scale T1. So this is actually the longest part of the whole experiment. It takes a few seconds. And yes, the signal is observed. You can find out these particular peaks, and this little width corresponds to the not just a perfect sinusoid, but a decaying sinusoid. Okay. So the solution, if you plot it, it will produce a whatever this signal, and this is a function of time, and this rate of decay will decide the width of the signal. So these are all things which are very well known for all oscillation systems, and you can all explicitly see them in the data. Okay. Okay. So now this is telling you that all the observables which you are extracting from the experiment are only single qubit population level. You are not measuring any correlations at all. Okay. And that, so that is connected with the fact which I mentioned, these populations fall off exponentially for n qubits. And this is one of the limiting factor of NMR, that you cannot handle large systems. Your observables are very much localized on individual levels. You can measure them, but the populations will go down rapidly as you analyze the number of systems, number of qubits. Okay. Yeah. So this is all the single qubit stuff, but it provides many of the important concepts. And the other thing which is connected with that, that only non-identity part of the density matrix that if you have any contribution to rho which is proportional to identity, it is not going to get affected either by the algorithm or by the measurement, for the very simple reason that evolution will always be of this particular form. If you put identity matrix, nothing happens to it. These two factors will just cancel out. So yes, there will be more generic states, but you have to look at only the part of rho, identity, subtract it out, and all the remaining terms which are proportional to various Pauli matrices, you can observe them as a function of time. Okay. So now the next part, yeah.
The rho is evolving with the density matrix is evolving with time.
Yes.
I x k plus 1k. What is that exactly?
This IST is the complete Hamiltonian of the system. Or this is observable you are trying to measure. It has two components, x and y, and it's quite common to write it as a complex number. That is why I put that I over there. But you can write it in a different language, and then you get cosine and sine, and you will pick them up with a Fourier transform. You do this, then you will write e raised to I omega t, which is a little simpler, whatever it is. That's all. But the point is that when you get a signal, you will not only measure its magnitude, but you will also measure its phase. Both are detectable. So now I can go to the next part, which completes this whole machinery, which is two-qubit operations. Single qubit comes from resonance. The measurement comes from electromagnetic induction, and these two-qubit operations come from the J coupling. That's the only thing which is contributing to it. Okay. And the simplest operation which we need is control naught or control z or one of those things, and that will make a universal set. Okay. Yeah. You have to keep in mind that the J coupling exists between neighbors, and so the two-qubit operation will occur only between those neighbors. You want to apply some longer distance two-qubit operation, you have to find some other solution. Okay. So the easiest one to work out is the diagonal operation, which is the control z. Okay. And in the matrix form, it is this operator 1, 1, 1, minus 1. It's easy to deal with this because it's perfectly symmetric, etc., and these J couplings are also fully symmetric, and so the mapping is a little bit easier. So I want to write down in terms of operators which involve these various spins, basically z at one qubit and z at another qubit, and there is a simple identity which can be used, and that is these are the terms be- which I want because they are the ones which appear in the Hamiltonian. Hamiltonian has single qubit Z coupling and this J coupling between neighbors. Okay. And well, why this is that? It's a kind of trivial thing. This is 1, 1, 1, 1. This one is a Z1 times identity, so it is 1, 1, minus 1, minus 1. This is identity times Z2, so it will be 1, minus 1, 1, minus 1. And this last stuff is Z1 times Z2, so it will be 1. It's basically a product of these two. 1, minus 1, minus 1, and 1. And then you put in all the plus and minus signs, so you will see this. Yeah, so this is plus, plus, and this is minus. So this is 3 minus 1 is 2, and that is a half over there. Here, two of them will cancel, and this and this add, which again makes 2. These two cancel. These two add make a 2. And this is minus 1, another minus 1 and 1, so it makes minus 2. So this is rather straightforward. And now using the identity of exponentiating the Pauli matrices, you can rewrite this thing as a product of the overall normalization, which is to take care of the phase, but that doesn't matter very much. But there are very specific angles. This is pi over 4, for example. And I have omitted all these identity factors. It doesn't matter very much. And because they are all Z, you can write exponential, but all these factors commute. So the order is not important. And to show that this actually is equal to that value, expand it out. So this is all these matrices square to identity, so you can write it as a cosine and sine, no problem with that. And cosine and sine will be of pi over 4, which is 1 by root 2. Okay. So that is where all these i's and all those things are coming in, but just let me do that. So this is 1 by root 2, and this will be cosine of pi by 4, which is I, and then sine pi by 4 times it looks like that. That should be okay. And this one is again another 1 by root 2. This is identity minus I Z1, and this is 1 by root 2 identity minus Z2. And you collect all the terms, and it should give you back this structure. So this is there is a what some e raised to I pi by 4, which is needed because, well, this root I is exponential of this object with angle pi by 4, which I have not bothered to write it explicitly, but that is what this is. And these are the exponentials of the other terms. But anyway, this is a identity, and I will not worry too much about normalization. There are all the root 2's, etc. But now if you multiply these terms, there should be 8 different products, and it should simplify to 2 times these 4 terms essentially. So let me, there is I here, all kind of things. So the 8 terms here are this identity from all the 3 terms, and then there should be another factor of identity. Did I put the angles properly? Yeah, it should come out, whatever it is. Otherwise, I have lost some factor somewhere. But there will be another identity term which will be Z1, Z2, one Z1 and one Z2 over here, and they will add up. So let me work it out. It doesn't look that complicated, but I can do it step by step. So this is half. There is a identity minus I Z1 minus I Z2 minus I and I square. So yeah, minus Z1 Z2. And then I multiply with this, and the 4 terms are okay, but somehow the phases are not quite correct. Let me see. So there is a I, but the Z1, Z2 is getting a minus I times it. Okay, let me, so it is 1 minus I times identity. Identity has 1 from here, and this times minus 1 gives minus I times identity. That is the one term. Then the quotient of Z1 will come from either directly with I and I or multiplying this with the cross terms. So let us do that. This identity times Z1 will give minus I Z1, and then this times this will give plus 1, and Z2 will get square, so it will look like Z1. That is a Z1 term. Then the Z2 term will be similar. It will be again minus I plus 1 times Z2, and then this last term, which is proportional to Z1, Z2, which has a quotient of I, and coming from this multiplying with this, and this multiplying with this gives minus 1 times Z1, Z2. Okay. So that is the product, and then this is 1 over 2 root 2 or something sitting outside. Yeah. The root 2 parts I have not included here. So there is 1 by the root I and 2 root 2. Okay. Yeah, so that looks more like what this thing was. This 1 minus I is this cancellation of the factor of root I. Root I is e raised to I pi by 4 is 1 plus I by root 2 or 1 minus I by root 2 inverse, e raised to minus I pi by 4 inverse, whatever it is. So that 1 minus I cancels this stuff. This, well, there's a root 2 here, and it takes out these 2 terms, and the half is whatever was sitting outside over here. So this is actually an identity produced by these 3 factors. And now the implementation part is to put these interactions for a specific amount of time. Okay. So these are e raised to I z times some evolution for fixed amount of time, because this is going to be the Hamiltonian part, and that now tells us that you should have this 2-qubit interaction for pi by 4, they call it just pi by 4 pulse. You have a Z1 interaction, another pi by 4 pulse, Z2 interaction with pi by 4 pulse. All of them you act. How you create Z1 and Z2 for pi by 4, we have seen. You can do this various juggleries with a single qubit stuff, so its axis is different, but that is fine. And there will be a pulse or other evolution of this J coupling for a fixed duration. Okay, so my time is up. I will complete this description next time. But this is essentially the crux of the matter, that the 2-qubit operations, you can convert it to some unitary evolution factors of very specific duration of time, and then you apply them in sequence to generate evolution.
So in an experiment for this Bluetooth operation, all of these pulses have to be applied at the same time.
They are applied to be applied in a specific sequence, and it's too complicated to do it manually. So actually you program a classical computer to figure out what all these pulses are, and then control the NMR apparatus by the classical computer. So yeah, and it's, I mean, all this machinery is well known. So the library for designing pulses exists, You just tell it that I want to perform this operation. The library routine will be dug out that, okay, this is the sequence of pulses for performing this particular operation. And it will just combine it, optimize all kinds of things automatically, and run the experiment.